Hello everyone, my name is Lucas and welcome to the Intellectual Bookshelf. Some textbooks teach you a subject, others teach you how mathematics itself should be written. For me, Gregory Naber's Geometry of Minkowski Spacetime belongs firmly in this second category. I first read this book during my PhD and for me, completely changed my expectations of what a mathematical textbook could be. It's rigorous without being intimidating. It's constructive, without ever feeling slow. And every chapter gives you the sense that you're discovering the subject for yourself, rather than simply being presented with the final results. So today, I'd like to tell you why I think this remarkable book deserves a place on every mathematical physicist's bookshelf. And actually, this isn't the first Gregory Naber's book I've talked about on the channel. I also reviewed Topology, Geometry, and Gauge Fields, Volume 1, Foundations. So if you enjoy this video, you might want to check that one out as well. I'll leave a link somewhere on the screen here. My PhD was in mathematical physics, more specifically in mathematical aspects of quantum field theory. So I was seeing so many different and incompatible theories floating around, like string theory, like loop quantum gravity, and higher derivative theories, and many others. I wanted to go back to the foundations and focus on what was the core assumption people were making that made these approaches unique and distinct. So I started picking foundational papers and books. I wanted both mathematical rigorous approaches and books devoted to discussing the physical principles as well. So I got some books that I thought were aligned to my intentions, like the ones I'm about to show you here. So I also got this one, Theory of Relativity by Pauli. Later I'll mention a little bit more about this. I got this book by Erwin Schrödinger, del espacio, la estructura del espacio-tiempo, space-time structure. Most of the books are either classic, or they are very mathematically driven, or focus on the principles on physical principles. This one also, it's this book by Anna Jijiban Das. I don't know how to pronounce this name, but yeah, The Special Theory of Relativity, Mathematical Exposition. This book by Couto and Limberopoulos, which is, my version here is in Portuguese. Introduction to Lorentzian Geometry, Curves and Surfaces. This one too. The Principle of Relativity this is just a collection of many foundational papers. General Relativity by Robert Wald. I'll mention a little bit more later. So I wanted to read the classics and those books that had a mathematically rigorous treatment and also treated physics at the foundational level. That's what I wanted to do. Okay, so let me briefly go through some parts of the book. The preface here, I think there are important things to mention. First, this is important to read. I think this summarizes a lot what the book is about. So it is the intention of this monograph to provide an introduction to the special theory of relativity that is mathematically rigorous and yet spells out in considerable detail the physical significance of the mathematics. Particular care has been exercised in keeping clear the distinction between a physical phenomenon and the mathematical model which purports to describe that phenomenon, so that at any given point it should be clear whether we are doing mathematics or appealing to physical arguments to interpret the mathematics. Okay, talking about some prerequisites. The background for chapters 1 to 3, the background required for an effective reading of the first 3 chapters is a solid course in linear algebra and the usual supply of mathematical maturity, he mentions. And then for chapters 4, a knowledge of some basic material from real analysis, such as the inverse function theorem. For the appendices, some familiarity with elementary point set topology. Yeah, the book contains 232 exercises. All of them are used somewhere in the text, so it's very important for you to work through the exercises. Okay, so before I talk about what I liked about the book, let me give you a quick idea of what you actually find inside the book. So, as its core, this is a book about the geometry of space and time. But what I really love is the way Naber approaches the subject, because he doesn't begin with Einstein postulates or begin with Lorentz transformations or just throw in equations at you. He starts with the geometry here. So slowly and carefully and very naturally, he builds the mathematical language you will eventually need to understand special relativity. And it starts essentially with affine geometry. And then he goes on. So Minkowski spacetime, he defines it mathematically. There are many remarks, along the text, and many exercises too here, you see. So there are many exercises, all exercise 1 to 4, exercise 1 to 5, exercise 1 to 6, 1 to 7. The exercises, some of the exercises are simple, others are more complicated. So you have, essentially you have theorems, and then you have the proofs. The proofs are very easy to follow. Most of them are very easy to follow. There are many images. After introducing and talking about Minkowski spacetime, the natural question is, what are its symmetries? So here, he talks about the Lorentz group, in 1.3. What I especially appreciated is that Naber doesn't present the Lorentz transformations just as formulas for you to memorize. It develops them as natural geometric transformations. And by the time equations appear, you already understand why they should exist. But the book doesn't stop there. Then he will talk about, time-like vectors and curves, and then space-like vectors, and then causality relations. Right, the causal structure here, space-like vectors, causality relations. So here, causality relations, he defines chronological and causal order. He uses the chronological order as the definition is x chronologically precedes y if y minus x is time-like and future-directed, and x causally precedes y if y minus x is null and future-directed. Many books use different notions of causal precedence. For instance, I think O'Neill uses a definition of causal precedence that is x causally precedes y if y minus x is either null or time-like future-directed. I think this is the definition of causal precedence in O'Neill and other texts. But anyway, this is just a convenience here. Yeah, and then there are many lemmas and proofs, and he introduces the causal automorphisms here. A map F from M to M is said to be a causal automorphism if it is a one-to-one onto, and both F and F inverse preserve the causal precedence relation. That is, x is causally precedes y if and only if f of x causally precedes f of y. So preserving the light cone essentially, right? But it's the same thing. You could, as an exercise, he actually asks you to show that you could, for instance, define causal automorphism as a map that preserve the chronological order instead of the causal order he defined. And then here, Naber states the famous theorem by Zeeman. So if you have a causal automorphism, then from M to M, Then there exists an orthogonal transformation L from M to M, a translation T from M to M, and a dilation K from M to M, such that F is the composition of these three. He carefully develops this, Zeeman's theorem, and you can understand all the development. So yeah, there are many things here. I'm not going to mention everything. Particles and interactions. Okay, yes. Chapter 2, skew-symmetric linear transformation and electromagnetic fields. The theory of spinors here. On chapter 3, representations of the Lorentz group, spin space, spinor algebra, spinors and world vectors, everything, bivectors and null flags. Chapter 4, I haven't gone through chapter 4 yet, Here, appendix A and appendix B. So again, these two appendices for me are already worth buying the book. I already, while studying the special theory of relativity, I already thought, why, if causality is the fundamental structure of spacetime, why do we simply assume the ordinary topology, right? Because, well, it makes no sense to use a metric here. There's no metric to induce a topology on Minkowski spacetime, really. Unlike Euclidean spaces, here you have a non-degenerate symmetric bilinear form G of index 1, and this bilinear form in itself will not induce a topology on Minkowski space, right? But you could use, for instance, I thought, well, you could use causality relation somehow to try to obtain a topology that has physical meaning. That's what I thought. Even before reading this book, I thought causality could be used to somehow induce topology on spacetime. I just didn't know exactly what to do, how to do it. And yeah, you could use, for instance, chronological order. You could use causal order, right? Not in this sense, because chronological order induces a strict partial order on Minkowski spacetime. And if you use the notion of causal order that is not this one, if you use the notion of causal order that is x is causally precedes y if y minus x is either null or time-like future directed, then this relation will induce a topology. You can use that to induce a topology on Minkowski spacetime. If causality is the fundamental structure of spacetime, why do we simply assume the ordinary Euclidean topology? Maybe you would think that Euclidean topology is not physical, is not natural, right, for Minkowski spacetime. Yeah, you could think about this in this way, and he does. He mentions Zeeman topologies here. So it's a different topology that is somehow induced, by the causality structure of spacetime. He also mentions the path topology, which I think was developed or used primarily by Hawking and McCarty. I'm not sure. The path topology, you could think about that path topology essentially as the basis for the path topology is take a time cone based at x and you intersect it with a ball, you ball with respect to the Euclidean topology centered at x with radius epsilon, and then you get this somewhat curved cone, and this is a basis. This can be shown to be a basis for the path topology. It is finer than the Euclidean topology. It's Hausdorff. He mentions some of the topological properties here somewhere. I don't remember where, but it does mention it. That it's, I think, well, it's Hausdorff. It's not difficult to see. It's first countable, but it's not regular. It's not normal, and it's not regular. So this is a very beautiful chapter that made me think about this, because I don't know. Because you could think, okay, maybe there is no physical relevance, right? Maybe you could treat the Minkowski spacetime with Euclidean topology. Maybe you could use another topology induced by the causality structure of spacetime. Will it somehow have any significance, some physical significance? Not in special relativity itself, but maybe if we are talking about I don't know, quantum gravity, some other unified theory, if you believe there is one, will that make any difference? I don't know. I'm not sure. Why this book is special for me? So this book is rigorous without being intimidating. That's what I mentioned already in the beginning. So you have precise definitions. It has a theorem proof style. The book is constructive, you know. So many textbooks, they will present the final picture immediately and ask the reader just to accept it. Naber does almost the opposite. Every new concept feels earned. That's how I felt. And by the time a theorem appears, you've already developed the intuition needed to appreciate why it is true. Exercises throughout the entire text. So instead of isolating, you know, hundreds of exercises at the end of each chapter, you will find them along the text. You know, so Naber actually inserts many of them exactly where they are needed, and that encourages active reading rather than just passive reading, I think. And clear proofs. The proofs are rarely, the proofs rarely feel like tricks. Instead, they feel like natural consequences of the definitions. Okay, I'm just going to mention, you know, to make some comparisons with other relativity books very briefly. By the way, if any of these books I'm going to show you now look interesting to you, I've left the links to all of them in the video description, including Naber's book, in case you'd like to add them to your own intellectual bookshelf. I already showed you some books here. Let me make small comparison comments and try to fight the urge to comment extensively on them at the moment. So here, this book by Das is also a great mathematical exposition, and I use it too, especially while thinking about separation theorems in Minkowski spacetime. Okay, so it is mathematical. It's a mathematical exposition, as written here, and it's a great book. Okay, but it's very mathematically driven, and there is not much motivation here. Okay, yeah, this book right here, Introduction to Lorentz Geometry, Curves and Surfaces. I have the Portuguese version. This book was written by Couto and Limberopoulos. It is also a great find, and it's purely a math book. It's very similar, very similar to Do Carmo's style in his, for you who know Manfredo Do Carmo, you know, Do Carmo's book Differential Geometry of Curves and Surfaces, which I also plan to talk about in future videos. It's very similar to Manfredo, to Do Carmo's book, and you know, the approach. Yeah, this, the principle of relativity. This is a collection of original papers on special and general theory of relativity, with papers by Lorentz, Einstein, Minkowski, and Weil. I believe this book should be required reading. It should be required reading for every physicist. It is absolute classic on relativity. You know, here is simply the Bible for general relativity, the best textbook on GR. You know, in my opinion. Of course, all of the books I'm showing here, I intend to talk about in the future. Space-time Structure by Schrödinger is another classic that is really worth reading. I came across this book by accident at a used bookstore. For me, it felt like Schrödinger was writing to convince himself of what was essential and what was just mathematical convenience. But it's really worth reading too. I want to mention this book, The Theory of Relativity by Pauli. Although this book is originally written in German, 1921, and the English translation it's from 58, it is still worth reading. Pauli is very careful in his logical and mathematical reasoning. So even for today's standards, I think it's really worth reading. Who should read the book? Well, I think if you're a mathematical student, a theoretical physicist, or graduate student, or anyone interested in geometry or in theoretical physics, really, I think you would really benefit from reading this book. If you're seeing relativity for the first time, I don't think that's the book to go. If you're looking for computational techniques too, I don't think this is the book for you. Now, if you've read this book, I'd love to hear your thoughts. Did it change the way you think about special relativity, geometry, or even mathematics itself? Let me know in the comments. And if you enjoy discovering books that don't just teach mathematics but change the way we think about it, I'd love to have you join us. Consider subscribing to the Intellectual Bookshelf. Thank you very much for watching, and until next time, happy reading.